you heard a little bit about me already. I'll just comment on a few of my St. Louis specific links, right? I have the MBA from WashU, and I taught briefly here as a lecturer at the biomedical engineering department because my PhD is in biomedical engineering. So I have a kind of interesting perspective for supply chain. And speaking of St. Louis, our company is a very St. Louis company, right? So who am I and who is SimpleRose? Here to talk to you about the supply chain today. We're an optimization solver company. We make the linear programming underlying device that runs the algorithms that do a lot of the supply chain solutions. They do many other solutions for a variety of problems, right? But it's very big in supply chain. And so this relates to supply chain very much into increasing productivity, increasing revenue, increasing profit, and of course reducing waste, reducing emissions, all the things that link up with sustainability. Our company is also a family company, might be of interest to some WashU people, and the founder is here, my father. It's always nice to mention it's a family company. I used to get math quizzes at dinner, so optimization research was not new to me. Right, so what are we going to do here today? First, we're going to talk about why does the supply chain matter? I mean, I'm sure everybody here knows the answer to this, right? But there's a huge amount of pressure to change from a variety of reasons, right? Like the environment and for profit and because your competition's doing it. Then we're going to talk about what currently exists, all these complex solutions, right? We've talked about a lot of them today. I work on the underlying complicated piece that solves the problems. And so I'm going to talk to you a little bit about heuristics, machine learning, and optimization and how they really work. And then last, we're going to talk about the supply chain redesign, why it's a continuous process that we never can finish, and why the rapidly changing conditions like the pandemic is something that, black swan theory shows us we might think is never going to happen, but we of course know is always going to happen. Right? So starting off with why the supply chain matters, right? Obviously, the one that's come up today, we've already talked about it several times, and I will talk a lot about how it links to all of our other motives, is the environment, right? It's no surprise that if you don't drive a truck, you don't pay for it. You don't pay for the maintenance on it, you don't pay for the fuel for it, you don't emit the emissions. It's not complicated, but it's complicated to see how it impacts your total supply chain, right? This is a similar thing to, all the waste generated with products and packaging, recyclability, right? If you don't make the product, you don't have to recycle it. If it's lighter weight, you don't pay to ship it. All these things go together, right? These relate to that profit pressure, right? You have to reduce emissions, take those trucks off the road. We don't want to own as many trucks. You want to buy less fuel, right? There's the largely apocryphal but sort of true story about FedEx only turning right. Like this saves money for them. It saves fuel too, but it saves money. Also, new technologies become available, right? We don't stay on Industry 1.0 because it's fun. We have to progress with new technology. And of course, the pressure to keep up with the competition, right? You're in an environment, you're in a competitive environment. You have competitors who are changing their supply chain. Their boxes are getting lighter, their trucks are getting more fuel efficient, they're flying less stuff and shipping it in larger batches together, right? You must keep up with them. The market is crowded and competitive, and people jump in with new ideas all the time, and they have a little gimmick where they're gonna bring this into the environment, and it's constantly growing, right? So this is exciting, but also tons of pressure, right? So all this pressure means we have to change. I'm gonna talk a little bit about a few of the companies that are doing this and why they're doing it and what they're saying about it. Right, this is a quote here from Boeing where they're talking about 100% zero emissions commitment by 2050. How are they doing this? They're redesigning their airplanes, right? X-66 initiative. They have a publicly available climate model that everybody can use to determine what their impact on the climate is. They have an Energy Star partnership that they win awards with every year, right? By making those tools available, they enable other companies who are saying, hey, what is my environmental impact, right? You need some tool like Boeing's climate impact model to start answering that, and developing it yourself is a huge uphill battle, right? So part of their commitment to doing this globally is public tools. Right, another one it's important in this area, right, AB InBev, right, they have a commitment to achieve net zero emissions by 2040. They have tons of smart agriculture initiatives. They have water stewardship initiatives. They have just absolutely tons of initiatives that touch both the environment and their profit, right? This is something that you see a lot. And they're, I think, the company that said, this is really a win-win-win for us, the environment, and the local grid, right? In this case, they're talking about energy usage. We reduce our energy usage. We pay less in utility bill. The local environment takes less of a hit. There's no problem with this, right? We're not being forced to be environmental. This is just a huge win. Right, you see this is, again, this is nice that I don't have to give a lot of Bayer quotes because we had the Bayer person come up and say all this right before me. I can just say, remember that. But this is another company where you're seeing the tie-in between the fragile supply chain, needing to understand and care for your supply chain, and like this kind of the theme you've heard before, we need this visibility, we need global perspective, we need to understand so much about our supply chain because it has some fragileness, it has some relationship to our environment, it has relationship to our profit, and this is going to really drive the world, the environment, and whether or not your company looks good on the balance sheet. Right? The last reason we talked about is, you got to keep up with the Joneses, right? The supply chain of tomorrow is always changing. They're already talking about Industry 5.0. I don't know if you guys have heard that one yet. I was still looking up Industry 4.0 myself, right? Industry 4.0 is about computers, robots, and the Internet of Things becoming important when all of your boxes have a little RFID on them and they know where they are. That's Industry 4.0. But then, the AI tools come out and people start talking about, well, hey, couldn't AI decide where all of our RFID boxes go for us? Let's invent Industry 5.0, and we're not even there yet. But it's coming. It will be coming. It's coming because we first of all, because people already write papers on it, right? So they've doomed us. But more importantly, it's coming because this is a continuous process, right? What we always do is we say, hey, if we know that, we can know something else even better, right? Just as a high-level thing, Industry 5.0 is big about cost optimization in that manufacturing process, right? Letting these fancy tools work at a more and more granular level, asking our robots and computers and our manufacturing devices to do these optimization steps internally as well as we do them externally and on the whole system, right, to start embedding optimization at all kinds of levels of our machines. Again, this is the future, but because it's coming, we have to start to plan for it. So how are we dealing with this currently, right? Complex solutions, we all know about. The ones that people have probably heard of most likely are heuristics, machine learning, and of course, like the underlying optimization, modeling, linear programming, deep mathematical, theoretical stuff that we'll get to in the end. All right, so up on the screen here, you'll see on the left a little kind of example of a heuristic. Right, when you're looking for the lowest point in that grid, you could search along the whole grid and you could keep track of every point. You could find the lowest point. Or you could do what this demonstration is doing and kind of throw a bunch of marbles in there and see where they land. And most of them are going to land in the lowest part. And as a heuristic, this is good. If you just count the marbles real quick, you say, oh yeah, most of them are in that spot. That's probably the lowest. Let's go there. It's very fast. It's much faster than checking every spot. Right? This is the kind of example of a heuristic. We need something quick and easy that we want to trade accuracy for speed, but we want it to be mostly accurate. Right? Machine learning, right? AI and machine learning are very good at doing what we're doing because they learn from us. Right? They see whenever people do this, I should do that. Right? They see what we're doing and they emulate it very well. And optimization modeling does that complicated thing where it goes through all the pieces and the places and it says, okay, what are the lowest point, and it checks them all and it says where the lowest point is and finds it and it says that's the one. Right? It requires detailed modeling, and I say it's embedded in other solutions, or maybe other solutions are embedded in it, and I'll talk about why that is in a minute. Right? So here's an example of a heuristic. Everyone probably has heard of the traveling salesman problem, right? This is a great problem that is known to be hard to solve with that big optimization approach. right? This is the 15 largest cities in Germany. I want to visit them all. And the optimization modeling approach says, okay, here's the perfect path. Here's the perfect path. And it's difficult to calculate. But honestly, a heuristic might be, well, I'm going to just start in Munich, and I'm just going to go to the closest city. And you'd say, how bad is this heuristic? Well, it makes an extra trip through Stuttgart, right? And you end up in Dresden. But if you're a traveling salesman, that might not be a huge deal to you, right? And so as a heuristic, this is a good solution for the heuristic, because they say, you know, an overnight stay in Dresden and a drive through Stuttgart, I don't need to wait for the machine to solve my algorithm. I can just use the simple approach of drive to the closest city. This is a classic heuristic. They're always very fast, and that's the point of them, right? You wouldn't take a heuristic if it wasn't fast. That's what you're trading the accuracy for. They're frequently combined with other techniques. Sometimes you'll use a heuristic to choose another technique or use a heuristic to set something. This is something that I think is really important that we'll see. These techniques are not mutually exclusive, right? Machine learning. This kind of slowly moving GIF on the right there is what's called a dropout neural network. It's a big, complicated way for a network to make a decision about all these different things in this layer. This is a great example of a machine learning network, because nobody here understands it, and it's just going to magically do something. That's a perfect example of what machine learning is. It's not interrogatable. It has this black box effect. Now, there are people who understand machine learning, of course, and one of the things they'll tell you is there's no free lunch. There's no algorithm that does everything. You have to choose which algorithm does which thing very carefully. It is a very well-researched thing, but no matter what we get out of the machine learning, it's very hard to develop heuristics from it, because we can't simply ask the machine learning algorithm, why is this the decision that has been made? We can throw different data at it and let it observe what we've done, and that's the only way we can train it to do something new. If we want to elicit new behavior out of it, we have to train it or allow it to train itself endlessly. Like we have to run it to do this. So this takes time. There's two good and bad things that relate to this. We have a lot of data in society now, right? It's everywhere. We have those RFID boxes, right? So we know where all the clothing in the store is and all that stuff. So there is a lot of data. But this network that I'm showing here is an example of something to avoid that last thing, overfitting. It really learns to do exactly what we've already done, right? If you sold a lot of red shirts last year, you should buy a lot of red shirts at the same time this year, right? It's going to very, very much overfit, and we know this, and so we have a lot of techniques to avoid overfitting, like dropping things out, but this is always something we're fighting against with the network. It learns what we do. We don't want it to learn too carefully, because what machine learning really does for us is generalize, right? If it learns pretty well but not too perfectly, it can say, well, you know, some color will be popular this year. We should stock up on whatever's popular. Why don't we find out what that is? And that's the extendable to similar situations, right? That generalizability is machine learning's great strength. All right, last thing I want to talk about is what I do. I hope it doesn't come through too obviously that I prefer this technique to the others, but I think that they are all important and they all inform each other, and that's something that's super important. This is something I said before. True optimization modeling is going to say, okay, to find the optimum of all the options, we must examine all the options, right? There's no real tricks about it. One of the kind of fundamental theorems of operations research at the deep level is some of these problems are difficult at a level that's proven to be not cheatable. There's no shortcuts, there's no tricks, there's nothing to do but check every spot on the graph, right? This means that high levels of complexity are usually involved with optimization modeling, and they do usually involve specialists like the people in this school who do supply chain, right? They have specializations in designing models like this because it's very complicated. But what we do with this skill set and this information is we build a detailed landscape of what's going on. And I've made a reduction here saying, let's say you have some inventory policy about how much you're holding, and you have some transportation time agreements that you've made, and there's some relationship to them with how much cost you pay and what contracts you take and everything. And optimization modeling can find where the lowest place for this is, and you can set it and do it. This is great, right? Those are what we're doing now. And so now we're going to finally talk about how do these all help us in rapidly changing situations? How do these all help us do something in this situation? What is the map that lets us out of here? And then lastly, we'll talk about like when something's truly new and no one's ever seen it before, how do we model it? So this chart I'm showing you here is a kind of model of, if you look at the top chart, the bottom charts are, when we're looking down on that chart, we say if the blue is very low cost and the red is very high cost, and on the left on that bottom there is what it used to be till the pandemic came, and the pandemic disturbs our environment, right? It changes everything about us. Well, I say everything. The old solution is still in there. It's kind of, if you look closely, you can see there's a little divot where we used to have our lowest cost. And when we keep doing what we're doing, what we'll see is that whenever we change what we're doing, we're going to pay more. But there's some other place distant on the new landscape that didn't used to be interesting to us at all that's cheaper. This is the kind of situation in the pandemic, right? Nothing fundamental changed about the world, but when so many costs changed, so many things were different, the environment was very different. So we're going to talk about how and why the different techniques work in these different cases. Right, so heuristics are going to spend their time looking right here, where our old minimum was, right? And it's going to check the local environment, and it's going to say, hey, no matter which direction I go, I'm paying more money. Maybe I shouldn't move from where I am. Now, there's different heuristics that might find a different way, but that's a common kind of heuristic that you might use. They also basically assume that the general shape of our thing hasn't fundamentally changed, and they'll frequently miss something that is, I don't know what to say except for distant from it in the graphic here, right? This activity involves different things than we used to be doing. It's pretty far from what we used to be doing. It's making different promises. It's holding different amounts of inventory, right? If we want to do machine learning with this, we have to teach machine learning about the pandemic, right? This is something that I think a lot of people experienced when the pandemic happened. We said, okay, well, what's this new situation? And we might start feeding that into a machine learning algorithm, and the next day it would be different. New factories were closed, new policies were implemented, things were reversed left and right. So every day you had to get new training data. And if, again, for machine learning, we need a nice chunk of training data. It needs to be fairly consistent. We need to be able to, iterate, even if we're bootstrapping, where we copy a lot of it and pretend it's different versions of the new thing. We need a supply of it. So we have to wait for the pandemic to happen to truly be able to model it through machine learning. And we might say something like, oh, well, there was a pandemic in 1912. Let's use that data. And then we're using, industry 1.0, 2.0 data in our modern system. It isn't informative at the level that we need it to be, right? So we need modern data with rich detail to get a good machine learning algorithm out of that, which is something that we will want to do. And then, of course, overfitting will be a huge problem when we have so little data, right? That's why we mentioned it earlier. The more data we have, the less that's an issue. But the more we rely on specific data, the harder this is for us. So optimization modeling is an attempt to give us a map, right? And in the pandemic type situation, we might have a very poor map. I've drawn some fun tetrahedron to icosahedron maps here, right? We might have a very bad map, right? You might have that pyramid map of the Earth at that early pandemic level with your attempt to model it with expertise who understand what's happening. But one thing that's important to remember is that what data there are, oops, that's the stop button. What data there are and what data we can iterate on are really important. Oops. So what we're looking for is a more detailed model, right? And the way we get that is by iterating through, by experiencing the pandemic, right? And then this data is the very same data that's going to go feed into that machine learning model and teach us our next heuristic, right? Iterating the model becomes the basis for some of these other techniques. Black swans. Is anyone familiar with the black swan theory? Black swans are this idea. Long ago, before Australia was discovered, people thought black swans didn't exist. They thought it was ridiculous. And they used to use it as an expression, oh, it's as impossible as a black swan. And then, of course, someone visited Australia and they found a bunch of black swans, and they're quite delicious, and they brought them back and they ate them. And it's kind of a joke now, and this Nassim Taleb is famous for saying, like, this is always going to happen. Whatever you think is impossible is generally going to happen. You cannot predict when it will happen, and you can't guess it your way out of it, right? And there's certain strategies he suggests about it. But this is a very important thing. If you're trying to think long term, you need to be thinking that there will be an event like this, but you don't know what it is, so you need to reserve some resiliency, and you need to not run your efficiency too tight just because it is going to happen, but what it is not really possible. My favorite fact about this is, of course, black swans don't exist, but all swans are born gray, except for black swans who are born white, because why not? The opposite of this, satisficing, right? We just stop the first time we find a solution. This is super common, especially in business, because our solution, when we find our first solution, we've become a profitable business. And we often stop asking, is there 10%, 20%, 30% more profit available? If we're into satisficing, we're like, whew, we made it. Don't change anything, right? This is a very common practice. Sometimes, it's a psychologically satisfying practice, right? We've been fighting our way uphill, we've been losing money, and we get to that point, and we don't want to change. But of course, the environment is changing, and if there's 10 to 30% more profit available or environmental emissions to cut or anything like that, right, it's just an opportunity that we're wasting. We're literally throwing that away when we do that. So the question is, does an existing model actually require this kind of fundamental change? Is it a whole new thing? Is the new normal really unprecedented, or does it just require new data? Is it a new version of operational excellence? Is AI and robots, are they really unprecedented, or are they just the newest tech innovation, right? Are geopolitics really truly unprecedented? Are ESG policies really truly unprecedented for us? Or are they just things that are becoming our new normals, right? All these things kind of float down over time. And the only thing that ends up being truly unprecedented is stuff we don't know about, right? Things that are a big question mark in the air. Things like the pandemic seem like they might be a completely fundamental shift, but then we say, really, it just changed all the prices of everything. We didn't have to add new places on our map to go. The canal blockage, right? It just changed the price of everything. It changed the distance of everything. It changed the costs and times of things, but it didn't reshape our whole landscape. Some things do, right? Some things do, and this is another kind of math joke that probably is not as common as I think from my table, right? But physicists used to say, okay, let's assume all cows are spherical, right? We got to start with something. We know things take up space. We know spheres take up space. We got a nice equation for it. Let's start with cows are spherical, right? And then over time, we'll get a more and more detailed description of the cow. And then, again over time, we'll say, hey, you know what, we don't need this much detail at all. We want to come back a little bit and pretend the cow's a little bit spherical because it's a little bit easier, right? This is how we model. It's iterative. It takes a lot of time. It takes understanding. It takes going back and forth between experts in one field and experts in whatever field we're modeling, right? Because very rarely is a operations researcher going to be an expert in the field they're interested in, agriculture, transportation, whatever. And of course, I said there's no shortcuts, only long cuts, right? Machine learning learns from optimization. Optimization gets its predictive data from machine learning, right? They're very much linked together. These techniques build on each other, they grow each other, they enhance each other. Because we use predictive technology for one, we use prescriptive technology for one. We say, what's the best we can do in the situation? What's the best guess we can make about the future? Those are very different questions, right? And machine learning is very good at answering the guess about the future, and optimization is very good at answering what should we do at this moment, right? And so all these techniques are built up, right? Data and statistics, predictive modeling, all this feeds into optimization, which then in turn feeds into a huge collection of data from society and validation and training and understanding, and then all of this comes down into our toolbox in the end, right? We have special words we use for math and meta-heuristics, where we say things like, we're gonna use a heuristic to decide which optimization algorithm we're gonna run. We're gonna use a heuristic to pick a machine learning model to run this on, right? They build on each other, they pick each other like that. So we have to remember what different techniques are good at, right? Some techniques are poor at adapting to the fundamentally new, like the heuristic and the machine learning. And they need to have something embedded into them by users who do the modeling step first, and then we teach the models those things, right? Likewise, models aren't magical. They can't build themselves, right? So where do we get that information to build the models? We have to develop predictive algorithms for machine learning. We have to develop all these expertises in big data and data collection and validation, not to be underestimated, right, if you've ever seen bad data. Right, so what can we do? The last thing, call to action. You can be involved, right? Find someone like me or Dr. Colas here and explain your business to us. Talk about it, right? Talk about formalizing the rules, right? Whatever we're doing, if we can formalize it, all these techniques can be brought to bear on it. If you can say, instead of a hand-wavy way of saying what we do, if you can commit to it and write down an SOP and we can quantify the steps of it, we can start to develop ways to understand it and put it in this global perspective to develop our, not only optimization, optimizing the procedure of it, right, but optimizing the way it fits into our whole business, the way it fits into our environmentalism and everything. And that means including stuff like formalizing your rules of thumb. Well, I just always such and such, right? Well, that's a rule that you've developed, and we can talk about how to put it in there. And the last thing I want to say, right, is optimization opportunities are everywhere, right? We talked a lot about sustainability, right? But these are things that happen in scheduling. These are things that happen in planning. These are things that happen in bundling. Several examples of each of these have come up. But basically, there's just so many of these chances to find an optimization. And every optimization is a chance to improve our environmental impact or our profit impact or the amount of labor we take or something like that, right? By bundling products together, by planning better, by grouping things, and by scheduling more efficiently, right? So continuous supply chain redesign is what I think is necessary. You're never going to stop finishing that, right? The environment is wild. The model will not stay still, right? The machine learning will need to be retrained. And in order to do that, we're going to leverage what already exists, right? We do understand a lot about our supply chain pretty well. We're going to model things when they're new. If we have a truly new thing, we're going to model a truly new condition. And I always say there's no substitute for sitting down and having people explain the situation, right? Machine learning model, much as I love them, they're never going to do that for us. They're never going to explain the situation in a way that we find satisfactory and interrogatable. And no matter what we do, we're going to keep doing it, right? Iteration brings continuous improvement. This is obvious. When we use a word like optimization, it sounds terminal, right? But it's always optimal for the moment, optimal for the situation. So this is continuous optimization.